All right, so here's the video that I promised doing a review, and I'm going to talk about the new group assignments as well at the end, just so we can talk about them, since we haven't talked about them in class. So first off, let's start off with the electric chapter. So we started off with electric force. So we said if we have two charged particles, here's my two charged particles of charges Q1 and Q2, separated by some sort of distance from center to center of R. Then the two will either attract or repel each other with a force magnitude F12, which is equal to the magnitude of F21. Means that it abides by Newton's third law, and they're actually in opposite directions, which finishes that, is then equal to Ke, which is our electric constant, times then the magnitude of Q1 times the magnitude of Q2, all divided by R squared. So this is the magnitude, where like charges equal a repulsive force, and then unlike charges equals an attractive force. So this is only true for 2-point charges. So this is true for 2-point charges. If I have more than 2-point charges, then we have to use the superposition principle. So which says then that the force on the ith particle is then equal to the sum over the jth particle, where it cannot equal the I, of then the force on I by j. So basically, in this case, again, if let's say I was equal to 1, then I would sum from 2 to 3 to 4 to 5 to etc., right? So again, as an example, if I is equal to 1, then the force on 1 would then be equal to the force on 1 by 2 plus the force on 1 by 3 plus the force on 1 by 4 plus etc. for how many that I have. So this guy is a vector sum where the total force would then point in the direction of the vector sum. So leave it that way. From there, we can then define the electric field. So the electric field then is equal to, I'm going to drop the limit part, but this is going to be equal to the force divided by the charge, which also tells me then that the electric force is equal to simply the charge times the electric field. So again, we spend a lot of time talking about this one as well, but basically the definition of the electric field is the force that a charged particle would feel at a given point, which means if we know the force that it would feel at a given point, if we simply multiply it by the charge of that charged particle, then that would tell us the actual force acting on that guy. So that's it, which then leads to the fact, for example, a point charge. So for a point charge, our electric field then is simply equal to the electric charge times the charge of that charge divided by the distance r squared in the r hat direction. So this means that if I had a positive charge, we would simply have electric field lines pointing radially away from it. That's what the r hat means in this particular scenario. So this is our electric field, where anywhere along a constant radius of r, the magnitude of the electric field is identically the same, but the direction, of course, will be different. And if I have a collection of point charges, again, we're going to use our superposition principle, which says that the total electric field at some point P then would be equal to the sum over I of the electric field from charge I at that point. So again, as an example, this is the same thing then as the electric field at point P is then equal to the electric field from charge 1 at point P plus the electric field from charge 2 at point P plus the electric field from charge 3 at point P plus however many other possible charges that I have. So again, it's just simply the superposition or the vector sum of all the possible electric fields from those charges, however many charges that I have. And then if I have a continuous object, then simply we chop this thing up into a bunch of small pieces and then sum over an infinite number of particles, which in this case means that we're going to do an integral. So in this case, this becomes equal to the integral of the differential electric field, which is then going to be equal then to what? Ke integral of dq divided by r squared in the r hat direction, where dq, again, we turn into a geometrical integral, which is then going to be equal to the line charge density times dl, and then sigma, which is the surface charge density times the differential area. And then finally, we have a rho dV, which is the volume charge density integrated over the volume, where we use the first one if we have a line symmetry. We use the second one if we have an area symmetry. And then we use the third one if we have a volume symmetry. So just kind of remind you what this means is we're going to cut out a small little section here. This is my DQ, right? So there's my DQ. And let's say down here is my point P that I'm interested in. So technically this is at point P. Then in this case, I draw my R. So my R again is the distance from that point to the charge. So technically it points from the differential charge to that point. And in this case, let's say I have a total charge in this case, Q, which is greater than 0. Then the differential amount of electric field from that piece of charge is then going to point along the line away from the object itself. Okay. So in this case, again, it's simply the superposition of an infinite number of charges, which means that we cut this thing up, consider the electric field from all the individual point charges, and then sum them all together, again, creating an integral. Well, that's simply that guy. So again, in this case, dq is some representative amount of charge. Great. R, again, is the distance from the point charge, or our differential amount of charge, to the position of interest. And again, here, what we want to look for is symmetry. So basically, we want to look for if there's anything symmetric that cancels with anything else. So meaning does a dq's dE cancel with another dq's dE. Okay. So we saw plenty of examples of this in class. So for example, if I was looking then at a line of charge, and then above the midpoint here, we had then our points of interest P. So when we chose our little dq on this side, then this guy gave us R was here, and then our electric field in this case pointed in this direction. So this is my differential electric field. Symmetrically on the other side, of course, we do have at the same distance this little dq here, which has exactly then the same R, but now our differential electric field points in this direction. So that means that by symmetry, the horizontal pieces are going to cancel, which leaves us only with the vertical piece here. So in this case, then we have to worry about finding the cosines and sines because we only want, in this case, the vertical portion, not the entirety of everything that we're going to integrate over. So good. So that's that guy. So we spent a bunch of time working on this thing here. And again, here, this is true. So we can use this for any shape, i.e. doesn't need to have perfect symmetry, unlike Gauss's law. We'll get there in just a second. Good. After that, that's when we focused on the second half of this guy, him. So that was pretty much about it. We did a bunch of examples of that. And then finally, last thing we talked about was the electric dipole. So let's talk about our electric dipole. So an electric dipole is 2 point charges separated by some distance d, which we promote to a vector. So this is d, where the magnitude of d is simply equal to the separation distance between the two. And then here they have equal and opposite charges. It looks like a horrible Q. So there we go. So it points from the negative Q to the positive Q in the opposite direction as the electric field, which always points from the positive to the negative. Excuse me. And then we define the dipole moment. Let's see, we use blue in this case, which points in the direction of D, so that our dipole moment is then equal to the charge of the positive charge times then the vector distance d between the two. What we did with this guy then is we put it into an external electric field. So if I had an external electric field in this direction, let's say here is my dipole moment P, so that these guys are oriented at an angle of theta relative to each other. What we showed then was that the torque on this guy is equal to the dipole moment crossed by the external electric field, meaning that the magnitude of this guy is then equal to the magnitude of the moment times the magnitude of the electric field times sine of the angle between the two. And then we also did the electric potential energy of this guy, which is then equal to negative the moment dotted by the external electric field which is then equal to minus the moment times the electric field times cosine of the angle between the two. And then, of course, the work by the electric field is then equal to minus the change of potential energy of the electric potential energy. So that's this guy. So that's pretty much all we did. Ultimately, we spent a whole bunch of time doing all this stuff. But ultimately, it's not too much stuff, right? So you got the forces between two charged particles, force superposition of many pairs of particles. And then you got your definition of the electric field, which also gives you the electric force in terms of the electric field. And then you have your point charge for the electric field. Superposition, again, when we have many possible different charges all giving electric fields. The Coulomb's law for the electric field of a continuous charge distribution. And then finally, we have our dipole moment, which then we found the torque and the energy for. So ultimately, not that many topics. So next chapter we looked at was a Gauss, or Gauss's law. So Gauss's law, this one's not going to take me much time, basically just says that the electric flux through some surface is then equal to the closed surface integral of the electric field dotted by the differential area, which is then equal to the amount of charge enclosed inside of that area divided by epsilon naught. Okay. So this is over the surface of that volume. So this thing is actually a 3D volume, but then we're integrating over the surface of that. So over the surface of the 3D volume, okay? Which is why it's a two-dimensional integral, because we're integrating over the two-dimensional surface area of that. But again, this thing has the caveat that it must have perfect symmetry. Meaning if it doesn't have perfect symmetry, you cannot use this. So our perfect symmetries are: one, spherical. Spherical is perfect by default. Two, cylindrical. But cylindrical is only perfect if it's infinitely long. So in this case, it has to be infinitely long. Meaning if it's not infinitely long, if it's finite length, then you cannot use this. And then the last one is, that should be a 3, planar. But again, it has to be a full plane. So meaning an infinite plane. So this only works for an infinite plane. Which means if I simply had a square sheet, for example, and I was looking for the electric field some distance above here, then we can't use Gauss's law. Because in this case, it has finite length of, say, L and L, right? So as long as it's finite in shape, except for the sphere, you cannot use it. Everything else has to be infinite in extent, okay? So again, the idea here is to what? Choose the symmetry. That best mimics the symmetry of the charge configuration. And then from there, we get to draw a Gaussian surface, which we choose. Then we choose a Gaussian surface. That mimics that symmetry, and then we do everything from that Gaussian surface. Let's see, that has the correct symmetry. Now, the reason we do this, as we spend a lot of time in this in class, is the fact that if we do that properly, then the electric field is constant everywhere along the surface, which means the left-hand side in that case, when it comes to the electric flux, is simply going to be equal then to the electric field, magnitude anyways, times then the surface area of the object, right? So that's the point of doing this. So let's kind of go over quickly some surface areas. I'm only going to do this for one spherical. And then 2, we'll get to the cylindrical. So in this case, the surface area of a sphere is simply the derivative of the volume. So that guy's 4 pi r squared. Great. And then in this case, the differential volume is going to be equal to the surface area integrated over dr. So this is going to be equal to simply 4 pi r squared times dr. And this will be necessary because in general, let's go back a slide, Q enclosed in general will be equal to the integral of the charge distribution or the volume charge density integrated over the volume. This is true in general, but if you do this in this color, but if rho is equal to a constant, then this thing just reduces down to the charge density times the volume enclosed. So this is the volume enclosed by the surface. So by the surface. So again, Q enclosed literally means the amount of charge that's enclosed inside of that Gaussian surface. So that's pretty much it that I need for that guy. Second one then is cylindrical. So we'll talk about cylindrical. So for cylindrical, we have to be a little bit more careful because there's technically 3 different areas, even though 2 of them are the same. So you have the end caps here. So the surface area of the caps is just that of a circle. So if this thing has a radius of r, then this is just pi r squared. And then you have the shaft portion itself. So the area then of the shaft is then simply equal then to what? The circumference, which is then going to be 2 pi r times the length, where this is some length of L, so that's going to be L. Okay. So here it just depends on the direction of the electric field. So if the direction of the electric field is parallel to the axis here, then you would use the end caps. If it is perpendicular in this direction, where this is the direction of dA, because remember dA always points outward, perpendicular to the surface, then you would use the shaft. So in this case, again, it's going to depend on what it is that I'm doing. So my differential volume. Now, in this case, if I'm integrating outward, right? So basically what I'm going to do in that case is I'm going to cut it up into a bunch of little rings that has a dr, which has a radius of r. So in this case, I'm just going to do what? The circumference of the ring, which is then going to be 2 pi r, times then the length of the object, because that's, again, surface area, a volume, and then I'm going to integrate that over dr. So this is, again, when it's talking about the radial direction. If I'm talking about the axial direction, in this case, then my differential volume would then just be equal to the cross-sectional area then of the cylinder, which of course is just pi r squared. So I'll keep doing it in that direction, pi r squared. But in this case, we're cutting it along the axis, which means that we're cutting it like this, which means that this is going to have a differential length in this direction. So then I'd multiply this then by dl to turn it into a volume. Right? So it just depends on the direction in which it is that I'm going. Do I go along the axis or do I go perpendicular to the axis? Again, radial, meaning perpendicular to the axis. And then finally, the axial, which means parallel to the axis. So again, hardest part here is basically, first of all, knowing all your surface areas, but we just wrote them down, so that's not going to be a big deal. And then determining exactly what is Q enclosed. And then you just have to pay attention to your geometries and all that kind of good stuff. But that's it. That's all it is for Gauss's law. So for Gauss's law, it's going to be one of these 3 different things. But again, it only works if I have perfect symmetry, which means for the second 2, it has to be infinite. If it is not infinite, it will not work. Fantastic. And then lastly, let's choose a different color. So I'm getting bored with that. Let's look at potential. So this is our potential chapter. So first off, we said that what? Work, at least the work done by the electric field, is then equal to what? The integral of the electric force dotted then by the differential length going from A to B. So just kind of remind you what this is here's my coordinate system. Great. It's called that X, Y, and Z. And then let's say this is my initial vector A, and then this is my final vector B. And then we have some pre-described path. So here's my pre-described path, where then DL is going to be the differential length across here. Okay. But we also know this guy then is equal to minus the change of potential energy. So this would be the electric potential energy. So that's this guy. Fantastic. So, which means that we can also write this then as equal to, using from the previous slides over here, using this guy, we could write this in terms of the electric field and the charge, which means I could finally write this then as minus Q, or sorry, with a plus sign here, sorry, Q times the integral from then A to B of the electric field itself dotted by the differential length. So that's this guy. From here, we can then define the electrostatic potential, where we define then the electrostatic potential V is then equal to the electrostatic potential energy per unit charge. So this thing has units of volts. Fantastic. So that means then that the change in potential energy, electrostatic, then would be equal to the charge times the change in potential. Good. So this means we can now use conservation of energy. So conservation of energy now simply says then that what? The change in kinetic energy plus the change of potential energy, in this case, electrostatic, is equal to 0, because again, there's no non-conservative forces, which means we have the change in kinetic energy plus the charge of the charge moving in the potential times then the change of potential is equal to 0. So this is our conservation of energy. Furthermore, using this expression here, we can then rewrite the change of potential, which again is equal to the change of potential energy per unit charge, as then equal to minus the integral from A to B of the electric field dotted by the differential length. So all this thing says then, again, is if I know the electric field, I can then determine the change of potential between 2 points. So that's what this guy says. And again, since I'm dividing by the charge, that just cancels out this charge here. Beautiful. Good. And then simultaneously, the inverse of this guy says that the electric field then is equal to minus the gradient of the potential. Beautiful. So that's this guy. Change the element. There we go. So good. So that's this guy. So from here, we can specifically look at what? Point charges. So now let's talk about the potential of a point charge. So the potential at a point P for a point charge then is going to be KE Q divided by R. So just meaning if this is my charge Q, and then this is my point P, and then this is my distance R between the two, then that's my potential at that point. Notice again, there's no absolute values on that. So in this case, we have to keep the sign of the charge. So if I have a positive charge, it's positive potential. If I have a negative charge, it's a negative potential. But again, this is the potential. Again, just be careful with this. This is relative to spatial infinity, where the potential at that point R is equal to infinity is equal to 0. Furthermore, if I have more than one point charge, then superposition tells me that the total potential at that point is then equal to the sum over all the possible potentials from all the possible charges. So again, as an example, this is going to be the potential at point P from charge 1 plus the potential at point P from charge 2 plus etc. Now, again, just to reiterate, this guy here is much easier to use than that of the electric field because it's a scalar, which means I don't care about direction. All I care about is the magnitude and the sign of the charge. That's it. And then finally, whenever we have a continuous object again, I'm going to do exactly the same thing. Let's choose some other colors. Let's go with the green spectrum here. Again, I'm going to cut this guy up into a small little charge, dq. I'm going to look at the point of interest. Let's call that my point of interest, P. And again, I'm going to draw a line, connects the two of those points together, some distance, R. And then again, we're going to use superposition to find all the total potentials. Let the dq's go to 0, basically, meaning we're going to chop it up into an infinite number of pieces and then sum them all together, which means that, as always, we're going to get an integral. So this says that the potential at point P is then going to be equal to the integral over all of the individual differential potentials, which is then going to be equal to KE integral dq divided by r. Again, there's no r hat because this guy is simply a scalar quantity, which means that I don't have to worry about directions. I don't have to worry about angles. I don't have to worry about components. We simply just do that integral and call it a day. And again, the dq's here are exactly the same as they were before. And that's it. That's basically as far as we got. So when it comes to potentials, again, we have this guy. We can define our potential this way. And then we can do conservation of energy again. We can find the potential between 2 points. As long as we know the electric field, or if we know the potential, we can find then the electric field by taking its derivative. The potential of a point charge. This superposition says it's just the sum of all the other ones. Again, this is relative to infinity, where again, the potential is 0. And again, even here, this is also relative to infinity, because again, we're using that of the point charge, which means that this also would be true only relative to infinity, where it's 0. So again, this thing is actually a potential difference, saying that this is the potential difference we would get by measuring with a voltmeter at this point P here, and out here at R is equal to spatial infinity, where our potential, of course, is equal to 0. So that's just what we call the potential at that point. But again, semantically wise, it's actually the potential difference between that point and where it's 0 at spatial infinity. So that's pretty much it. So what to expect? So let's talk about what we should actually expect on the exam here. So let's go all the way back. Let's go back. So let's use this color palette for an example. So this will definitely be a long problem. So this would be what I'm going to call long problem number 1. Basically, it's going to be this mixed with conservation of energy. So this guy here. So this would be also part of long problem number 1. So basically, the examples that we did in class with the charge moving through parallel plates and looking for the deflections, things like that, that's basically what we're looking for here. So you're going to use the fact that you know the electric field to find the force, to get the acceleration, to then find the deflection. But then you're also going to accelerate it through some sort of potential difference to find the velocities and things like that. So that's going to be long problem number 1. Let's talk about long problem number 2. So long problem number 2 is, as I talked about before, definitely going to be Gauss's law. So this would be long problem number 2. So here you would have some sort of charge configuration, probably multiple sections where you got to find the electric field in each particular part. So again, we did some examples like that, but so for example, the one that we did where we had a cylinder, had some charge distribution, and then shrouding that guy was another cylinder, maybe hollow in this case, which also has a different charge configuration. So then you got to find the electric field on the inside of this one, in between the two. And then let's say this one is actually a little bit thick. So it's going to be something like this. Okay. So in that case, then you would also want to find the electric field in this area as well as out here. So in this case, there'd be 4 different parts. And then, of course, as I promised, there'll be some sort of plotting where you plot the magnitude of the electric field versus the position. So good. So that's the second one. So we got one more to talk about. And then the last one would be either, but this is either, this guy here, which is the integral of a continuous charge distribution. So find the electric field at one point. So this would be long problem 3. Or its equivalent, which would then be finding the potential at a particular point, and then using this guy here to find the electric field. Okay, so this would also be part of long problem number 3 on the or part. So I'd expect to do either of the two. So again, either have a continuous charge distribution where you'd have to find the electric field, which means you'd have to do angles, find symmetric parts, blah, 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 where, or this one, where you find at the same point the potential at that point, again, relative to spatial infinity. And then you would use that guy, which we don't have to do angles and directions and etc., to then find the electric field by simply taking its derivative. So So those are going to be all the different long problems. Fantastic. Thing really has terrible colors, doesn't it? Okay, so let's choose this now. So let's talk about the short answer ones. Use that color, whatever that is. So the first short answer one I would expect would be with forces. So basically superposition. So like this guy. So this would be short answer quick calculation number 1. So basically superposition of forces. So basically forces between multiple point charges and then finding the force on one of those guys. Again, looking for symmetries and blah, blah, blah. And of course, that guy uses this, the definition of Coulomb's law. Another one would be this one. All right, so short answer quick calculation 2. So this would be a dipole in an external field, and then calculate then the torque or the potential energy or any of these kind of things. I would look to do that in unit vector notation, which would be awesome. And then finally, of course, all this here is part of long problem number 2, I should specify. And then the last one I would look at would probably be either this guy. So basically finding work from a non-constant force, because if it was force just equal to a constant, that'd be too easy. So I would say either this one, short answer quick calculation, number 3, or something to do with point charges, maybe superposition of point charges or something like that. So, or this one as short answer quick calculation 3. So I'd expect one of those two. That would basically be it. So that pretty much covers everything. I think everything's on here. Let me kind of follow. Yeah. So the only thing I wouldn't worry too much about would be the superposition of electric field, because you're already doing that with the integral anyway. So yeah, so that's it. So that's what I would expect. Again, make sure you practice these different integrals and things like this. Know when you have to do this versus doing Gauss's law, all that kind of good stuff. And yeah, so next thing let's talk about is then the group assignments that I just posted. So let's talk about those. So let me bring those up on my computer here real quick. And then we can talk about those. All right, so I put up 4 actually. So let's talk about the first one here. Go. Once this opens, then I got to switch screens. You can do it, I think. Probably should open this before I actually start making a video, but that's okay. We'll make it through. Yes, grant access. Wow. Okay, that was brutally taking forever. There we go. Okay, so let's share my screen again so you don't have to see my beautiful face. There we go. Whenever you are going. Okay, so in this case, the first one says that you have 2 electrons are fixed 2 centimeters apart from each other. And you can draw that in a minute here. And then a third electron is shot in from spatial infinity and then stops midway between the two. What is its initial speed? So this is just conservation of energy, but here the potential is given by the potential of point charges. So I'll talk about that in a second. Oh, I didn't put up 4, I put up 3. Okay, sorry, discounted. The second one here, this one, so this is, you just have this rectangle, and then you have all of these different charges on here, and you just want to know what then is the total potential at the center at point P here from these 6 total number of charges. Now, one to pay attention to is the fact that unlike electric fields, if the signs of the charges are the same and are equidistance away, they actually don't cancel. So for example, Q2s here, the total potential at this point actually wouldn't cancel, they would actually double. They would just sum together at this point. The reason for that is, again, when we had the electric field, if this was a negative charge, from this one, his electric field would be pointing upward, his would be pointing downward. which means the magnitudes would be the same, but they'd be in opposite directions, so they would cancel. But again, since we're dealing with potentials, which are simply scalars, that means that we can't use the fact that directions are opposite because there is no direction, which means the total potential here from these two would just simply be the sum of the two, or that would be twice of one of them. Now, the ones that would cancel are these two, the Q3s here. So even though the electric field wouldn't cancel, because here the electric field, this is a positive charge, would be pointing towards the corner here. This is then a negative charge, which means it'd also be pointing towards the corner, which means the total electric field from these two would simply double. However, when it comes to the potentials, again, all we care about is the magnitude of the distance, which would be the same, and the sign of the charges. But since this one has a positive charge, this one has a negative charge, so the two potentials would sum together to give me 0. So again, just be a little bit careful when it comes to potentials. It's not like electric fields where the direction, again, doesn't matter, so these guys wouldn't cancel. So that's the first two here. Let me quickly bring up the other one, assuming this guy decides he wants to work. There we go. So this is then just a continuous charge distribution, and then finding potential at the center points here from this continuous charge distribution. So the total angle at which this rod, which has a constant linear charge density, is bent is the angle of phi. So this is all happening at a constant radius. So all you're doing then is, again, integrating to find what is the potential here. So there's different ways you can do this, but if you want to use this particular geometry, that means you would integrate then from, in this case, minus phi over 2, because this is a minus phi over 2, to then the final phi over 2 here, which would then give you that guy, which means the total angle, again, would just be phi. And then just like we did when we talked about this in class for the electric field, this then bent rod would then, your DL, you would rewrite in terms of arc length. So you just kind of cut that guy out there. So again, let me kind of draw pictures for those second ones here, the first one and then the third one, so we can kind of see what this is supposed to do. So the first one out of these said that we had one electron here, we had another electron here. These were separated by a distance of d, where d was 2 centimeters. We're going to take a third electron somewhere out here, which is, again, from the midway points here, some distance of r is equal to infinity, which means there's no potential out here. So it starts off in potential equal to 0. And then this guy is going to shoot off in this direction with some initial velocity, v0, so that it eventually stops here at the midway point where there's the final electron, where my final velocity be equal to 0. So this is the picture for this guy. Again, it starts off in 0 potential region, but it's going to finish off not in a 0 potential region. So he's got to find out what is that final potential. And then, yeah, just got to go about it that way. So nice and kind of easy. You're just looking for what is the initial velocity necessary to do that. And then the third one, again, here is my coordinate system. Beautiful. So this is my X and this is my Y. And then this is a radius R here. This is a radius R here. So this total angle is phi, which means this angle here is phi over 2. And then this angle is minus phi over 2. And then you're going to cut this thing. So here's my bent rod, again, at a constant radius here. So here, all I mean is if this is my little dq, which then has a length of dl, right? So the length of this guy is dl. So that then corresponds to what? This right to here, this right to, whoops, not a great picture, but that's okay. This right to here. So then you would slice out through here. So this is the differential angle. So then by arc length, this is then just going to be equal to the constant radius times that differential angle sliced out through there, where this then here would then be equal to that angle of theta. So in this case, it's easiest to do as simply an arc length integral. And then this one's nice and easy. It kind of pops out real quick. So these are, again, the group assignments here. So these are the remaining ones. Sorry, we won't have a chance to work on these in class, but we ran out of time. Things happen. So anyways, so tomorrow then, Wednesday, we'll start working on some new material. because we got to start covering that before we actually get to the exam. And then by the time we finish the exam, so on Friday, we'll have to continue on with the new material because, as always, we're already behind. So awesome. So anyways, yeah, just let me know if you have any questions. Other than that is all the stuff you need for the exam. All those electric fields and stuff that we actually derived, don't worry about those. Those will not rear their ugly heads on the exam. You just have to know how to do them, right? So basically the procedures of which we did to get to those answers, because you'll have to basically do the same thing. So, okay, so that's it. And like I said, if you have any questions, just let me know. And other than that, I'll see everybody in class and get ready for the exam. Bye.